How do you get self-interested AI agents to actually work together? I mean, it's one of the biggest puzzles in all of artificial intelligence. But a new paper from Google might have found a surprisingly simple solution. It shows how cooperation can emerge not from complex hand-coded rules, but from something much more fundamental: diversity.
So here's how we're going to break it down. First, we'll set the stage with the core problem, the cooperation puzzle. Then we'll look at the really clever training method these researchers came up with. After that, we'll dive into the results, which are pretty fascinating. Then we'll unpack the step-by-step reason why it works, and finally, we'll talk about what this all means for AI teamwork down the road.
All right, let's start with the big challenge itself, what we're calling the cooperation puzzle.
Really, it all boils down to this question. If you have a bunch of AIs, and each one is just trying to get the highest score for itself, what stops them from just backstabbing each other for a quick win? How do you get them to a point where they actually trust each other and cooperate for a bigger payoff? That is the fundamental problem this paper tackles. To study this, the researchers used a classic scenario from game theory called the Iterated prisoner's dilemma. It's basically the perfect laboratory for this kind of thing. In every round of the game, two players have a simple choice: cooperate or defect. Now, the tricky part is that defecting looks really tempting in the short term, but if both players can just trust each other and cooperate, they both end up way better off. The so-called Nash equilibrium, where neither player can do better by changing their strategy alone, is for both the defect, even though it's a worse outcome for everyone.
And this little chart, the payoff matrix, is where you can really see the dilemma. Look at that top left box. You both cooperate, you each get a point. Great, that's the best outcome for the group. But then your eyes drift over to the bottom left. If you defect while the other person cooperates, you get 2 points. That's the temptation. The danger, of course, is that if you both defect, you both get nothing. The whole game is about trying to land in that top left box.
And what makes this so incredibly hard in AI is this idea of non-stationarity. Okay, imagine you're trying to learn a game, but the rules are constantly changing. Why? Because the other player is also learning and changing their strategy at the exact same time as you. Your best move is a moving target. For most standard learning algorithms, this is a total nightmare.
So, how did the team at Google get around this? Well, they came up with a really interesting training method, one that's designed specifically for this kind of constantly shifting environment.
You know, a lot of the older ways of trying to solve this were super complicated. People would hard-code assumptions about how other agents might behave, or they'd create these complex systems with meta-learners teaching naive learners. This paper just gets rid of all of that. No built-in assumptions, no different classes of agents, and they use standard off-the-shelf learning techniques. The real magic isn't in the algorithm itself, but in how they train it. They call the method mixed pool training. It's pretty straightforward. First, you've got your main learning agent, which is based on a sequence model, kind of like a transformer that can look at the history of a game. Then, you throw this agent into a bunch of games. Half the time, it plays against another smart agent just like itself. But the other half of the time, it's up against a much simpler, more random kind of agent. And here is the absolute key to the whole thing. The agent is never told which kind of opponent it's playing against. It has to figure it out mid-game just by watching the moves.
Okay, so that's the setup. It sounds simple, almost too simple. Does it actually work? Can this really lead to cooperation? Well, let's take a look at the results.
And the results are, well, they're kind of staggering. Just look at these graphs. They show the cooperation rate for a couple of different learning algorithms. The solid lines, both the red and the blue one, are our agents from the mixed pool training. And as you can see, they just rocket up to nearly 100% cooperation and stay there. It works, and it works incredibly well.
But how do we know for sure it was the mixed pool and the uncertainty that did the trick? Well, that's where the other lines come in. The researchers ran what are called ablation studies. Basically, they took away the secret ingredients to see what would happen. The dotted lines, that's what happens when you train the agents only against other smart agents. And the dashed lines, that's when you just tell the agent who it's playing against. And look, in both cases, the result is a complete collapse. They just defect against each other over and over. This is the proof that co-player diversity and the need to guess the opponent's strategy, that is the magic here.
So we know it works, but the really cool part is understanding why it works. What's the actual mechanism here that's turning these selfish agents into cooperative partners? Let's dig in.
The researchers uncovered this beautiful three-step causal chain. It all starts with diversity, which forces the agents to adapt. That very same adaptation then creates a vulnerability. And, believe it or not, it's that mutual vulnerability that ultimately leads to cooperation.
So let's walk through that one step at a time.
Okay, step 1. Because the agents are always playing against this mix of smart and simple opponents, they're forced to become really good at figuring out who they're playing against and changing their strategy on the fly, right in the middle of a game. They have to learn to read the room, so to speak.
And you can literally see that learning happen right here. This chart shows a single game. Look, when our agent plays against a simple, always defect opponent, it quickly learns, okay, I'm just going to defect back. But when it faces a tit-for-tat player, it adapts again and realizes, oh, if I cooperate, we'll both do better. It's adapting its behavior in real time.
Now, here's the crazy twist. When an agent gets that good at adapting, it also becomes predictable. And if you're predictable, you can be exploited. This incredible adaptability actually opens the door for a clever opponent to extort the agent, to basically manipulate it into an unfair deal.
And this graph shows exactly that happening. The researchers took one of their super adaptive agents and basically froze its learning. Then they trained a new agent, the red line, to play against it. And what happened? The new agent learned to totally exploit the adaptive one, basically bullying it into cooperating while it mostly defected, getting a much higher score.
So what do you think happens when two of these powerful, extortion-capable agents face off against each other? You'd probably guess it's just an all-out war, right? Constant defection, but that's not what happens at all.
And this is the final, most elegant piece of the puzzle. When two of these agents meet, they both try to extort the other. They try to get that unfair advantage. But they quickly realize that the other guy is just as smart and just as ruthless. Neither one can bully the other, and so they rapidly steer each other toward the only stable outcome that benefits them both: mutual, high-reward cooperation. It's like the threat of mutually assured destruction leads to a peace treaty.
So let's zoom out. What does this incredible, emergent solution really tell us about the future of AI and how we build intelligent systems that can work together? You know, I think this quote from the paper's conclusion just says it perfectly. What's so powerful here is that this isn't some fragile, brittle solution that needs tons of custom engineering. They're showing us a scalable path. It suggests that we can teach AIs complex social behaviors just by using standard tools and carefully designing the environments they learn in.
So, to wrap it all up, the big takeaways are pretty clear. First, you don't need a bunch of complex machinery to get cooperation. The secret ingredient, the real critical piece, is co-player diversity. This forces the agents to learn on the fly, and in doing so, they end up teaching each other how to cooperate. It's a scalable path forward, a lot like how we train huge foundation models on diverse data from the internet, and it really opens up some new possibilities for creating more socially aware AI. And that leaves us with a really fascinating thought to end on. If a behavior as complex and, frankly, as human as cooperation can emerge from a simple principle like diversity, what else is out there? What other complex social behaviors like negotiation or maybe even empathy are just waiting for us to create the right environment for them to be learned? It's an incredibly exciting future to think about.